Okay, we start for the new lecture on the single phase system. That's right, for the single phase system. And also I show you the sort that you would like to find the density of fluid energy property, because the pressure solubility of the fluid we can grab from many reference books, like for early chemical engineering handbook. You can find from the library, or you can find from the ebook. I think I will post to you. I'm not sure. I will check again for the early chemical engineering handbook. And also another, and also I give you some the electronic book, and also and actually this in HUT you cannot drop this. Okay, you can use for website from National Institute for Standard and Technology. Because you can find the property of or thermodynamic property, physical property, chemical property of the substance in the single phase, multiple phase, like liquid, solid, gas, or liquid gas system, liquid solid system. Something you can find from this reference book. For today, I will introduce you about the liquid and solid. The first, liquid and solid density. If the mixture, for this case, liquid and solid, I mean the solid dissolved in liquid, like solid dissolved in liquid, like syrup. Syrup means the sugar dissolved in water. That's right. For this case, we call the solution in liquid phase, but the component have two components: water and sugar. That's right, water and sugar. And also another common, like brain solution. Brain solution is really like salt, sodium chloride dissolved in water. This is also the solution. It's like how we estimate this density. We have two techniques. You can estimate from the equation, or you can experiment, like you can measure the density. For the equation to estimate the density, we propose for two equations. This equation is 1 over average density equal to summation of xi divided by y. Xi means the weight fraction. For example, if we have sugar and water, sugar and water, it should be 1 over average density equal to weight fraction of sugar divided by density of pure sugar, plus weight fraction of water divided by the density of water. Okay, for the equation, we can use the property of pure component to estimate the mixture component. You can estimate the average density of syrup, the sugar dissolved in water, by using of the density of sugar and density of water, and then the composition of water and sugar. And also the second equation, we can calculate the average density equal to summation of xi below I. The mostly for this case, we use when we know xi in terms of weight fraction. That's a weight fraction. But for this case, we use more of the mole fraction if we know the weight fraction. For equation 1, we have some comment. Is based for the mixture with a similar molecular structure, like for hydrocarbon mixture, something like this. For the alcohol mixture, something like this. This is the best for the similar structure. And also this picture, we show an example. Example, the density for sulfuric acid and water. This is for sulfuric acid and water. This is ethanol and water. That's right, ethanol and water. We have some equation 1 and equation 2. The black color is the experimental data. But alcohol and water, for this case, is the methanol and water. It's the best fit between the experimental and equation. That's like equation, but for sulfuric acid and water, equation 1 is the best. That's like equation 1 is the best. which fit well with the experiment, but there are some errors when you use the equation, second equation. That is, for example, we can estimate from the equation like shown in this slide, or you can directly measurement. That's right, directly measurement. Okay, the next I would like to talk about the gas or perfect gas, ideal gas. In this case, I will introduce you only the basic, because I think you study in basic chemistry. That's right, basic chemistry. Ideal gas or perfect gas. That's right. The ideal gas and perfect gas is mean the gas that follow the rule of PV equal to nRT that you study in high school in the first year graduate. That's right, first year student in high university. That's right. Okay, we can express in terms of PV equal to nRT, or in terms of rate, like PV dot equal to N dot RT. V dot is a volumetric flow rate. N dot means molar flow rate, something like this. R is the gas constant. That's right, gas constant. This equation we can explain in terms of PV equal to RT. It is the specific volume. This means the volume divided by the mole, something like that. Okay, for the ideal gas, that's right, the ideal gas, the standard state that at 1 mole of ideal gas at 0 degrees Celsius and 1 atm. This is the standard state. 0 degrees Celsius, 1 atm. That means the volume of ideal gas at 1 mole is equal to 22.415 liter. This is the standard state. And also the gas constant. The gas constant is the unit of the pressure. That's right. Multiplied volume divided by mole, multiplied by temperature, or the unit of energy by mole and temperature. This is the unit of that's right. Okay. And ideal gas, which is the work well under the some condition. That's under some condition, it may be above 0 degrees Celsius and pressure below 1 atm. This work well for ideal gas. If it's far from 0 degrees Celsius or 1 atm, it may be considered as the real gas. We cannot use the PV for nRT. That's like PV for energy. And sometimes how we can accept this ideal gas? Okay, we can calculate the error based on X ideal minus X2 divided by X ideal. Right. For example, if the absolute error is less than 1%, okay, we can assume that gas is the ideal. Or we can assume by the specific volume is V ideal equal to RT over P is greater than 5. Okay, we can assume this the ideal gas. For the atomic gas means gas with 2 atoms, or 20 liters per mole for auto gas. That's right, for auto gas. Okay, for this case, the error, that's right, the property that you calculate PVN, that's right, of ideal gas. The error when you compare to the true or the real gas, it should be no more than 1%. Okay, if it's no more than 1%, okay, you can assume that is an ideal gas. That's right, that's the ideal gas. And also you can correlate the specific volume. That's like the specific volume, like liter per mole, in terms of molecular weight divided by density. Like molecular weight is gram per mole or mass per mole. Density is gram per liter. Gram cancel, you get liter per mole. It's the same unit. That's that. Specific volume equivalent to the molecular weight divided by the density. And then you can calculate density of the gas equal to pressure multiplied by molecular weight divided by MRT. But for this case, you have to use the average molecular weight. Okay, and then we talk about the standard system, that is the standard temperature and standard pressure. Right? If we know like PV equal to AR equal to RT, P as standard state, V as standard state equal to RT as standard state. And then you can compare between the actual state and standard state. That's right, actual state and the standard state when the number of moles equal, something like that. You can PV, NS equal to 1, that's right. NS equal to 1 for the state. You can correlate the relationship between the actual state and the standard state by PV divided by PS, VS equal to NT divided by TS. Because this is also N divided by NS. Because NS equal to 1, you can cancel. That's right. PV equal to nRT divided by PVS equal to nRTS, something like this. NS equal to 1. R equal, that's how you can cancel that. Finally, you get PV divided by PS, VS equal to NTS. And this table shows you some condition of the standard state. We have 3 unit system, right? SI unit, CGS unit, American engineering unit. The standard state for SI is 0 degrees Celsius equal to approximately 273 Kelvin. That's right. The standard state pressure is equal for all units, is 180. That's right. For CGS also the same temperature, but for American engineering, it's 492. Thank you. That's right. And volume at the standard state, SI is in terms of cubic meter. That's right. CGS is in terms of liter. American in terms of cubic feet. That's right. And mole is the same but different unit. 1 mole, 1 mole, or 1 pound, something like this. And it did show you the conversion factor. You can change from standard state in cubic meters per mole to liters per mole to cubic feet per mole from this relationship. That's right, from this relationship. For this case, we provided a standard cubic meter, SCM, ATP, that's ATP and standard temperature and pressure. That's HCF is means standard cubic feet, something like this at ATP. Okay, the SCP means standard temperature and pressure. That's right. SCM is like standard cubic meter, standard cubic feet, something with the name of it. For example, right, for this case, we would like to calculate the volumetric flow rate of this steam. That's right. Of this steam that calculate from the standard state condition. Okay, for this steam is butane at 360 degrees Celsius at 3 atm absolute. That's right. This steam flow into a reactor at the rate of 100 and 1000 kilograms per hour. Okay, please calculate the volumetric flow rate of this steam. That's right. By using the standard state condition. I think from previous equation like this, you can use this equation to convert, that's right, from the standard state to the actual state. Okay. Right. From PV divided by PVS equal to NT, right? Okay, you can in terms of the flow rate, that's right. PV dot divided by PS, VS equal to N dot T over TS, and then you can calculate V dot. This is a volumetric flow rate equal to N dot VS T over PS and divided by P. That's right. You know TS standard state. You know PS standard state. You know VS the standard state. That's right. And for this case, you know temperature. You know actual temperature, actual pressure. You know the flow rate. That's right. You know the flow rate. Okay, the mole of this. That's right. The mole of butane. You use this flow rate. This mass flow rate. That's right. N dot molar flow rate of butane equal to mass flow rate divided by molecular weight. This is the mass flow rate. This is the molecular weight of butane. That's right. C4H10 you can approximately C is carbon. That's right. 12 multiplied 4 plus 10 approximately is 58, something like this. And then you can calculate molar flow rate of butane. And the temperature is 360 get plus 273. That's right. You get 633 Kelvin. And pressure at 3 atm. Okay, you know N dot, you know T, you know P. You substitute all this equation into this, and volume at standard state, PS TS, you can collect from this table. Collect from this table. Okay. This is the N dot. N dot. This is the standard state volume is 22.4 cubic meter per kilomole. And temperature actual is 633. Standard state is 273. Standard state pressure is 1 atm and actual pressure is 3. You get volumetric flow rate. That's right. You get volumetric flow rate. Okay, for this example, we give you an example how to calculate the volumetric flow rate based on the standard state data. You use the standard state data to calculate the actual data. Okay, for this case, we talk about the effect of temperature and pressure on the volumetric flow rate. On the volumetric flow rate. Okay, for this case, we have 10 cubic feet of air, air with 10 cubic feet at 70 Fahrenheit and 1 atm. It heated to 610 Fahrenheit. That's right. The pressure is compressed. Compressed means increase in pressure from 1 to 0.5, from 70 to 610. This is the two state. That's right. Initial state and final state. Okay. For this case, the question is determine the volume. That's right. At the final state. The final state. Okay, we can draw the process or draw the diagram like initial state, power air. That's right. We don't know. Okay, this is unknown n, and V1 equal to 10. Initial state we mean state 1. Okay, T1 equal to 70 Fahrenheit. P1 is 1 atm. Okay, the final state n, because this is n initial and n final is the state. For this case, the mole of the gas is the same. And V2, we don't know the volume of say final state. You know the final temperature, you know the final ATM. Okay, for this case, we can use the relationship between final state and initial state. So initial state we mean state 1, final in state 2. You can use the ideal gas PV equal to nRT. That's right, PV equal to nRT. Okay, P2, V2 equal to nRT2 because n is constant for this, R is constant. Right. PV1, nRT1. Okay, you use the ratio of these two states. PV2 divided by PV1 equal to nRT2 divided by nRT1. N cancel. That's right. You get this relationship. You get this relationship, and then you can calculate V2. You can calculate V2. Okay. V2 equal to V1, P1 over P2, T2 over T1. You know already for this. You can calculate the final volume of this. Okay, this gives you an example of the information from the standard state. That's like if you know the actual state, you can compare to the standard state. If you know to the two systems, the first state and second state, like this example, okay, you can use the relationship between the two equations of ideal gas. That's right. Okay, you can use this information. The third example, for this case, we use the standard and two volumetric flow rate. That's like the flow rate of methane at 285 Fahrenheit and 1.3 atm. That's right. The flow rate is, this is the temperature, this is the pressure, and the flow rate is 3.95 multiplied 10 power 5 SCFS. SCFS means standard cubic feet per hour. This is at standard state. That's right, at the standard state. Okay, calculate the molar flow rate. Molar flow rate means mole per time. That's right, mole per time. And the two volumetric flow rate. Okay, for this case, we record the standard state. We record the standard state. We know the standard flow rate is 3.95 multiplied 10 power 5 cubic feet per hour. Cubic feet per hour. But you know the standard state, how many volume. That's right, in the standard state. You can look at this table. This is table in the American Engineering Unit 359 at the standard state. 359 cubic feet per 1 pound mole. It's like 1 pound mole equal to 359 cubic feet for the standard state of gas. And then you can calculate mole, like molar flow rate. You can convert from volumetric flow rate to molar flow rate at standard state. Okay, and then you use the relationship between the two systems. The two systems, the system at 255 1.3 atm and the standard state. Okay. For this case, the standard state is state 1 and true state is state 2. That's right, true state is state 2. Okay. For standard state, this is the temperature at standard state. This is the pressure at standard state. This is the volume at the standard state. This standard state based on American Engineering Unit. That's right, American Engineering Unit. We use this is the standard state for American Engineering Unit. We state this is state 1. Right, this is stage 1. Okay, what is state 2? State 2 is the actual state. The temperature is 285. We can convert to Rankine is about 745 Rankine, and the pressure is 1.2. Okay, what is V2 for this case? What is V2? Right, and you can calculate V2 from the relationship is like this, the same. That's right. V2 equal to V1 T2 divided by T1 P1 divided by P2 with the same mole. That's right, the same amount of mole. Okay, for this case. Okay, for this case, you can calculate the volume. For the 3 example, we use the ideal gas PV equal to nRT to calculate the actual state compared to the standard state. Or if we know the true state, we can compare these two states directly. Okay. And the next one is I talk about the ideal gas mixture. Previously, we talked about the pure gas. That's right. PV equal to nRT for the pure gas, only one gas, one single phase. Okay, now we talk about the ideal gas mixture. When we talk about the ideal gas mixture, the pressure that incorporate or indicate like partial pressure. Okay. This is the partial pressure. That's right. Would exert by the mole of gas A. That's right, mole of gas A. And VA, this is the volume of gas A. That's right, volume of gas A in the mixture. PA is the pressure or partial pressure of gas A, right? Of gas A. Okay, for this case, you can use the PV equal to nRT also, but PA total volume equal to mole A RT. T is the total temperature of the temperature. This is the equation that to calculate the partial pressure. The partial pressure means the pressure of component A, component B, component C in the mixture. And also you can calculate the mole fraction of each component. It's calculated from the partial pressure of component A divided by the total pressure. This equal to mole A divided by total mole, equal to YE. And then you can calculate partial pressure equal to mole fraction multiplied by total pressure. If you know the total pressure of the system, you know the fraction of gas, okay, you can calculate partial pressure. Right, partial pressure. And also the total mole, that's right, the total mole fraction equal to 1. Equal to 1. The total pressure is come from summation of the partial pressure. PA plus PB plus PC plus CD, that's right, equal to P. And you know, right, PA equal to YAP, YBP, YCP, that equal to YA plus YB plus YC. All of this multiplied by P. That's right, we get this equation. This is we call the Dalton law. That's right, the Dalton law. Let's talk about the partial pressure of the component in ideal gas. That's right, the Dalton law is the ideal gas mixture. That's right, the total pressure calculation based on ideal gas mixture. We use the Dalton law. Okay, this for ideal gas mixture. Okay. But for more expression, we can call it like for gas. I forget the volume fraction and mole fraction is equal. For this, we can divided by PVA equal to NART. Previously we talk about the PA, P equal to NART, but also we can talk about the PVA equal to NRT. That's right. We divided by total, the PV equal to NRT. You get divided by this term. You get VA over V equal to NA over N equal to Y. That is the same. Mole fraction of the gas equal to the volume fraction. That's right. You can calculate YA equal to VA over V, NA over N, or PA over P total. That's right, P total. This is, we call this Amarkat law, and also it's only for the ideal gas. That's right, only for the ideal gas. I talked to you already. For this, is the volume percent equal to the mole percent for this gas. Volume fraction equal to mole fraction. And also equal to pressure fraction. That's right. Also, this is equal to PA divided by P total. Right. Please remember, this is only for ideal gas. That's right. Ideal gas at low pressure, and the pressure temperature is higher than 0 degrees Celsius. This is only for ideal gas. Okay, in this example, we talk about the material balance that we apply for the single phase. Single phase means only gas, only liquid, only solid. That's right. Or it may be liquid solid, but solid is dissolved in the liquid. We also form only phase, liquid phase. Liquid phase. Okay, for this case, we talk about the material balance around evaporator and compressor. As you know, right, evaporator, we use this equipment to concentrate the solution. Concentrate means you increase the concentration of the solution. That's right, of the solution. How to determine the concentration? For example, we have the sugar dissolved in water, or sodium chloride dissolved in water. That's right. If we would like to increase the concentration, for this case, in terms of evaporation, we have two components like water and sugar. For this case, we evaporate water out. That's right. We evaporate water out. When amount of volume of water decrease, the concentration will increase. Right. Because the concentration is calculated based on the mass or mole of solute divided by the total volume. Right. When the total volume decrease in terms of solvent, you will increase the concentration. This is the function of the evaporation. And the compressor, right? The compressor is the equipment to transport fluid. Right? We would like to transport gas from one location to the other location. We use compressor. And if we would like to transport liquid, we use the pump. Right? We use the pump. We will study this equipment in the operation in the detail, how to design. Okay, for this subject, we only apply the material balance for equipment. Okay, for the compressor means the input and output, the pressure will increase. That's right, will increase. Okay, we look at the detail. For this case, the liquid acetone is fed at a rate of 400 liters per minute into heat chamber. For this case, we call evaporator. That's right, evaporator. And then it evaporates to the stream of nitrogen. That means the product of this evaporator. That's right, the product of this evaporator will mix with the nitrogen stream. That's right, mix with the nitrogen stream. Okay, the gas leaving the evaporator also is diluted with the mixture of nitrogen. Okay, after the evaporation, this mix with nitrogen. That's right, we have nitrogen feed too. That's right, feed at the beginning to the evaporator and also feed to the product of evaporator. Okay. And both of product from evaporator and nitrogen mix together and then feed to the compressor. That's right. Feed to the compressor. The flow rate for this case, the flow rate of nitrogen equal to 219. That's like 19 cubic feet per minute as an state. Okay. and the combined gas are then compressed to a total pressure of 6.3. That's right. That means the pressure at the outlet of compressor is 6.3 atm. Gate pressure. That's right. Gate pressure. If you calculate based on the ideal gas, you have to convert from gate pressure to absolute pressure with the temperature of 322, 25. Partial pressure of acetone, that's right, is 501 mercury. And atmospheric, for this case, atmospheric pressure is approximately 763 millimeters mercury. Okay, this is the information. From the information, you can draw the diagram. That's right. Okay, we have the evaporator. We have the compressor. The feed to the evaporator. We have two streams. That's right. Feed off liquid acetone and feed off nitrogen. That's right. Feed off nitrogen. We don't know the volume of acetone. We don't know the mole of acetone. Okay, we represent by V1 and N1. You know the temperature. You know the pressure. And the volume or volumetric flow rate of, sorry, this is, okay, this is the acetone, this is the nitrogen, sorry. Okay, we don't know the volume of nitrogen, we don't know the mole of nitrogen. We know only the pressure and temperature. Okay, the second stream is liquid acetone. We know the volume of liquid acetone. We don't know the mole of acetone. That's right, we don't know the mole. Okay, these two feeds to the evaporator and the outlet of evaporator mix with the nitrogen at this point, and then feed to the compressor. N4 is the mole of the gas outlet of the compressor. Y4 is the mole of acetone. 1 minus Y4 is the mole of nitrogen. We know temperature, we know pressure, we know partial pressure of acetone. That's right. Okay, the question is, what is the molar composition of stream leaving the compressor? Calculate Y4 and 1 minus Y4. That's right, the composition of acetone, composition of nitrogen. Okay, the second one, what is the volumetric flow rate of nitrogen? Enter the evaporator, that means V1. What is V1? That's right, what is V1? If we know the temperature and pressure of the nitrogen. Okay. For this case, I think we can get, like, we can calculate the N3 and N2 directly. I think because we know the volume flow rate of acetone. That's right. We know the volume flow rate of nitrogen. You can use the molecular weight or density to convert from the volume to mole. Okay. Now you use the two information. You can calculate N2 and N3. That's you can calculate N2 and N3 directly. And also N4. That's right. You can calculate N2 by density. You can calculate N3 by density information, and also you can calculate Y4 by the partial pressure, because this is ideal gas. That's right. This is ideal gas. You can calculate fraction of acetone by the partial pressure of acetone divided by total pressure. That's right. Okay, from this information, you can reduce the unknown from 1, 2, 3, 4, 5, 6. No. That's right. But now you can calculate N2, you can calculate N3, you can calculate Y4. Now it's 3 unknown. That's right. This is the information you can use the degree of freedom analysis for that case. Okay, you can calculate N2 from the density. You can calculate N3 from the equation of state. That's right. You can calculate Y4. Then you make the balance. That's right. You make the balance to calculate N1 and N4. And then you use the ideal gas equation to calculate N1. Okay. Now you can solve for that. Okay. For this case, you calculate first by N2. That's right. N2 is the mole of acetone, liquid acetone. That's right, in molar flow rate. You know 400 liters per minute. And then you can find the density of acetone. Okay, you can open from the textbook that I upload to you, or you can find from the browser internet. what is the density of acetone. That's right. At the specified temperature and pressure. Okay, for this appendix, we get 0.79 gram per cubic centimeter, and then you can convert the unit to gram per liter. You get this. Okay, this is the volume of acetone in terms of permitted flow rate. This is the density, and also divided by the molecular weight of acetone. You get N2, that's the molar flow rate of acetone. Okay, the next one you calculate the mole fraction is Y4. Y4 equal to partial pressure of acetone divided by total pressure. Okay. Partial pressure, you know, the total pressure you have to calculate. That's right. For this case, you know the pressure is 6.3, but it's gauge pressure, not absolute pressure. That's right. The absolute pressure equal to gauge pressure plus atmospheric pressure. Okay, the atmospheric pressure for this example, we know this is the atmospheric. A different unit, you have to convert the unit. That's right. Okay, the absolute calculate equal to P gauge plus P ATM. This is the P gauge is 6.3. Right? You know 1 ATM equal to 760 millimeter mercury. This is the conversion factor. Okay, finally, you get total pressure is 5,550 millimeter mercury. This is the total pressure. And then you can calculate Y4 equal to PA divided by total. You know PA is 501. Okay, that you get the YA. YA means the mole fraction of acetone. That's right. And then you can calculate mole fraction of nitrogen equal to 1 minus Y4. Okay, now you know Y4, you know Y4 fraction of acetone, fraction of nitrogen. And also N3. That's right. N3 is the feed of nitrogen to the product of evaporator. You know at standard state. That's right. You know at standard state. Okay. This is the volumetric flow rate at standard state. And also you know the volume at the standard state. This is the volume at standard state per 1 mole. That's right. You compare to the standard state. Okay, you can calculate the molar flow rate of nitrogen feed to the product of the evaporator. You get N3. Now you know N3, you know Y4, you know N2. You can make the material balance. That's right. For this case, input minus output plus generation minus consumption equal to accumulation. This is the steady state. That's right. 4 in, 4 out continuously. Okay, we can cancel accumulation. And there is no reaction. That's right. There is no generation or no consumption because there is no reaction. Okay, finally you get input equal to output. Okay, the first one I balance on acetone. Okay, we back to the flow chart. What is acetone? If we make the overall balance, that's right. For overall balance, we have two feed, not 2 feed, 3 feed. That's right. Feed V1, feed this, and feed this, and 1 output. But if we consider acetone, only 1 feed acetone and 1 output. That's right. Okay, acetone. Okay, you know N2 already. That's right. You know N2 already. N2. That's right. For this case, acetone is N2 equal to N4 multiplied N4. N4 is the total mole of at the outlet multiply the mole fraction of acetone to get acetone. Okay. Balance on acetone, N2 equal to N4 Y4. You know N2, you know Y4 already. You can solve for N4. That's right. You can solve for N4. Okay, you get the molar flow rate of acetone at our output is 60,400 mole per minute. Okay, and then you make the overall mass balance. That's right. Overall mass balance the same. Input equal to output. That's right. Input equal to output. Okay, how about the overall balance? N1 plus N2 plus N3 equal to N4. That's now you know N2, you know N3, you know N4. You can solve for N1 directly. Yeah, and then you get N1. And then you know N1, you can convert N1, that's right, to the volume, right, to the volume by using the ideal gas equation, PV equal to nRT. because you know T, you know pressure, like you know volume at standard state, you know P, you know mole, you know temperature at actual state, right? And then you can solve for V1. That's right. The V1 equal to N1 Vs divided Ns Ts, T1 Ts, Ts, T1. Okay. N1, you know, right? This is N1. This is V at standard state. And this is the temperature, actual temperature, standard temperature. That's like standard pressure and actual pressure. You can calculate V1. Right? You can calculate V1 for the case. Now you can use the information for the single phase. That's for single phase. The first that we talk about the liquid and solid mixture. For this case, more the solid dissolved in water, dissolved in liquids. You consider it one phase, aside one phase, but two components. And also we talk about the gas. That's right. Gas is only one phase, but sometimes there's more than one component. Like this example, we have the acetone gas after evaporator. That's right, after evaporator, and nitrogen gas, something like this. And also we use the ideal gas to calculate the volume, the mole, something like this. I think this information can help you for the make the material balance, because this is we give you the last example. That's right. The last example we talk about the material balance for evaporator and compressor. You can apply the degree of freedom analysis. That's right. Degree of freedom analysis for this case. We have like N1, N2, N3, N4, Y4. That's right. 1, 2, 3, 4, 5, 6 unknown. And you know information that you know the volume of liquid, you know the volumetric flow rate of the nitrogen, you know the partial pressure, that's right. You know the partial pressure, and also you know the condition at the feed of the nitrogen. We have 4 information. That's right. We have 4 information. That's right, and 6 unknown. Right. You get about degree of freedom 1, 2, 3, 4, 5, 6. Okay. 6 unknown, 2 information, and 2 balance. That's right, 2 independent balance. You can solve that. That's right. You can solve it with 0 degree freedom. Okay, this is the example of mass balance. That's right. Previously, that's why we talk about the mass balance. That's right. And also this chapter we talk about the another information based on thermodynamic of the single phase. That's right. If we know the state, we know the volume, we know the ideal gas system, we know the ideal gas property. We can use this information, help you to solve the material balance. That's right, to solve the material balance. Okay. Do you have any question for the example? I will break for maybe 10 minutes. That's right, before we will talk about the multiple system.